Hi Cynthia, how are you?
Oh, not too good. I heard the results came back and I have to come back in to get it checked up with you.
Yes, that rash on your lower leg. Yes, it looks like it's mild cellulitis. That's a bacterial infection. So I'm going to prescribe you an antibiotic known as flucloxacillin.
Okay.
So you're going to have to take a 500 milligram tablet, one tablet 4 times a day on an empty stomach until all finished.
Are you kidding me? There's no way I'm going to be able to take all of those 4 doses. I work full time and on an empty stomach. I have to eat all the time because otherwise I get a bit hypoglycemic. Isn't there another option? Surely there is.
No, unfortunately there isn't for this particular infection.
With modern day technology, you'd really think there would be another option for hardworking, busy people like me. Have you ever experienced this with any of your patients? Giving them a medication which unfortunately they just can't comply to. Well, here at the Monash Institute of Research, the researchers have come up with a new formulation of flucloxacillin. Currently, the immediate release formulation is not able to satisfy patient compliance, and that leads to poorer health outcomes within the patient community. The researchers here have been able to get over the biopharmaceutical, physicochemical, and formulation problems, as well as any manufacturing issues, to come up with a controlled release formulation that will better allow patients to comply with this medication, promising better therapeutic results. Now we will head to a panel discussion where the researchers behind this development will talk about the improvements in the formulation and how they've come up with such an amazing product.
The team here at Monash University are interested in making a more patient-friendly oral formulation that not only improves patient compliance, but also increases the chance of successful treatment. But before we go into too much detail about our new product, we would like to give you an overview of the physicochemical properties of flucloxacillin and will demonstrate that there are several features present that can be manipulated into making a more patient-friendly formulation. Flucloxacillin is an acid-stable molecule which has a relatively good bioavailability of approximately 50 to 70%. It satisfies Lipinski's rule of 5 and thus appears to have relatively good molecular properties, which is an indicator of oral activity. It has a polar surface area of 138 angstroms, which is an indicator that the molecule is neither too polar nor too lipophilic and will therefore be able to cross biological membranes. It has 4 rotatable bonds, which is good for intestinal absorption, as is ideal for the molecule to be relatively rigid with less than 10 rotatable bonds. Flucloxacillin is a weakly acidic drug and has a pK of 2.7. Hence, at the site of absorption, which is in the small intestine, with a pH of approximately 7, it will be predominantly ionized, promoting dissolution and solubility. We have formulated the drug in its salt form as flucloxacillin sodium in order to increase its solubility. And the improved solubility is due to sodium salt increasing the micro pH environment around the acid drug particle, thereby increasing the extent of ionization. This significantly increases the rate of dissolution in the gastric acid environment and therefore increases the absorption of the drug when compared to its free acid form. And solubility of flucloxacillin is very important as the drug is required to be in solution in order to cross biological membranes and be absorbed. So overall, we can see that our drug has good physicochemical properties which can be manipulated and optimized for our new formulation product.
There are 3 main mechanisms for which this can be done: dissolution-based, diffusion-based, and osmotic pump mechanisms. FluCRo is a diffusion-based system where the drug is found in a reservoir surrounded by an insoluble polymer that controls how much water can enter and then the rate of soluble drug that can exit. Matrix systems are also a mechanism of diffusion-based control, as they can be made of either soluble components that release the drug as the entire matrix dissolves, or insoluble components that require solvent to enter and then dissolve the drug, the solid drug, for release. For FluCRo, we decided to use the matrix mechanism as we found it was easy to incorporate into our design. We chose hydroxypropylmethylcellulose, or HPMC, a widely used, comparatively cheap polymer, in order to keep costs of the consumer as low as possible. In terms of excipients used, hard gelatin-like capsules were utilised in order to appeal to a wider patient market. Those who oppose the use of normal gelatin for personal, spiritual, or religious reasons can generally safely take the hard gelatin capsules as an alternative. In addition, our controlled release formulation contains the currently used magnesium stearate as a lubricant, and various colours in order to differentiate the capsule. FluCRo is designed around delivering both immediate and controlled release flucloxacillin so that the MIC plasma levels are reached relatively quickly and are then maintained for the length of the therapy. When developing a controlled release formulation, there are several different formulation factors that can influence how the drug is released from the administration dosage form, and it's crucial that they're considered in this design. We had to consider how our dosage form would be hydrated, how water would diffuse into the system, and then how the drug would dissolve inside the system and then diffuse out into the systemic circulation. For controlled release formulations, at least one of the previous 4 steps has to be rate limiting to a degree the drug release is sustained for a long period.
To incorporate both immediate and controlled release flucloxacillin into FluCRo, we had developed a design of having a hard gelatin type capsule containing a mix of IR and CR pellets. The pellets are both manufactured through the extrusion and spheronization process. This involves the respective dry ingredients being mixed before a vehicle is added, forming a pliable wet mass which can then be extruded through dies to form uniform cylindrical rods. These rods are then placed in a spheronizer bowl, which moves in a toroidal or rope-like motion, essentially going round and round in circles, to spin the rods at such a rate to form into spherical pellets. These pellets then dried in a fluidized bed dryer before being filled in the appropriate ratios into the capsules and then being sealed. Now, the final aspect we had to consider when designing this improved flucloxacillin formulation was the biopharmaceutics surrounding drug absorption, distribution, and elimination from the body. As flucloxacillin is a beta-lactam antibiotic, it works in a time-dependent manner, and it is therefore essential that the plasma concentrations are maintained above the minimum inhibitory concentration, i.e. the MIC, for the greatest percentage of time. In terms of absorption, while flucloxacillin is acid stable and will not be degraded in the stomach, its absorption can be reduced by the presence of food in the gastrointestinal tract, lowering the peak serum concentrations. Ideally, for our controlled release formulation, it will be maintained above the MIC for as long as possible as the drug is released from the capsule in its 2 separate components. Distribution for flucloxacillin would theoretically be limited by its high protein binding. As we all know, a drug must be in its free, unbound form in order to be distributed to the site of action, which specifically for flucloxacillin is the site of infection, i.e. the skin. Flucloxacillin is 92% protein bound. However, this is not a clinically relevant problem as it has a low minimum inhibitory concentration for its susceptible bacteria. Therefore, only a small amount of free concentration is required for sufficient activity. The current immediate release forms are available and that you're prescribing to your patients currently reach after a 500 mg single dose of 0.8 to 1.1 milligrams per litre concentration. All we have to do in our controlled release formulation is to aim for similar sustained concentrations in the plasma for a similar level of efficacy. One of the key biopharmaceutical barriers to our controlled release flucloxacillin product is a short half-life of 3/4 to 1.5 hours. It is mainly renally excreted, and although this means that the immediate release formulation requires that annoying 6-hour hourly regimen of taking the tablet, this may be of benefit in our controlled release product because accumulation would not produce toxic levels, minimising any side effects that may result from such a situation occurring, such as liver toxicity, which can be very bad for the patients. In terms of bioequivalence, we have determined that it is not bioequivalent, so it cannot be used interchangeably or substituted for the IR formulation. So just imagine being able to prescribe for your patients a formulation of flucloxacillin containing the same 2 gram daily dosing that can be given either 2 times or 3 times a day, leading to the same serum concentrations, giving the same effectiveness as the current formulation, just minus the hassle of thinking of solutions to increase compliance in your patients.
Now that we've heard about the developments in drug delivery for this product, let's see how the patients have reacted to the new controlled release formulation of flucloxacillin, FluCRo.
Actually, I've heard about a new product that you only have to take 2 capsules twice a day on an empty stomach.
Well, if it's only 2 capsules and it's only twice a day, I think I can deal with that even if it's on an empty stomach. I think I'd be able to comply with that.
That's great. I'll write you a prescription now.
Thank you.